In this video we're going to have a look at a simple analogy for the effect of temperature on the position of equilibrium. So in this analogy we're going to take a house, and inside my house I've got my person. He's got two bits of equipment that they can turn on. They could turn on this thermal energy absorber on the left. That is a totally made up thing, but we can assume from the name that it's going to absorb thermal energy from inside the house. The second thing they've got in there is a radiator that I'm sure many of you will have, and that obviously heats up my house. How does it do that? Well, it transfers thermal energy into my house. So let's now impose a change on the temperature inside my house. Let's imagine, for example, it's a super hot sunny day. Now, if it's a super hot sunny day, which piece of equipment is my person going to turn on? Well, they're certainly not going to turn on the radiator and make it even hotter in the house. So probably to cool things down, they're going to turn on the thermal energy absorber, which will remove some of that extra thermal energy inside my house due to the hot weather outside. Take a second example. Let's imagine perhaps it was a super cold day, snowy, got a nice snowman there. Which piece of equipment are they going to turn on in this case? Well, if it's a super cold day outside, the temperature inside my house is going to decrease, meaning the thermal energy inside my house is decreasing. So to oppose that change, turn on the radiator, and we're going to increase the amount of thermal energy in my house again. So in both cases, when we've subjected my house to a change, the person inside my house has turned on the piece of equipment that's going to minimize or oppose that change. And how does that relate to chemistry? Well, in chemistry we come across something called Le Chatelier's principle, which states that when we subject a system to a change, the system responds to minimize that change. So let's consider a kind of chemistry example. Let's take a box containing some gases. We've got A and B are my reactants, C and D are my products, and importantly we need to know which direction in my reversible reaction is exothermic and which is endothermic. So in this example, and it might be different for different reactions, the exothermic reaction is the forward one, and the endothermic reaction must therefore be the reverse one. So let's now impose a bit of a change here. Let's increase the temperature of my box, the amount of thermal energy in my box. How would we do that? Well, we could heat it up with a Bunsen burner, for example, and let's consider what my system will do to minimize that change. So by heating the box, we're putting more thermal energy into the box. How can my system reduce that amount of thermal energy? Well, it can move in the endothermic direction. Equilibrium will move in the endothermic direction, meaning we're going to get more of that reverse process happening and absorbing thermal energy from inside my box. And what effects that going to have? Well, the concentrations of A and B are going to increase if that backwards reaction is occurring at a greater rate. Therefore, my products, C and D, they're going to experience a decrease in concentration. So overall, what's happened? Well, if I increase temperature, my equilibrium is going to always shift in the endothermic direction. And that might be forwards, might be backwards. In this specific example, it's that backwards reaction. That's the important one. Okay, let's try the opposite change then. How about if I were to cool my box down? So decrease the temperature inside my box, decrease the amount of thermal energy in there. How could I do that? Well, could you put it in an ice bath, for example, put my whole box in the ice bath to cool it down. So what's going to happen then? Well, the thermal energy in my box is going to decrease if I stick it in an ice bath. And we've just said the system will respond to try and minimize or oppose that change. So in order to increase the amount of thermal energy inside my box, we must move or shift equilibrium in the exothermic direction. And that's going to result in the concentrations of C and D increasing, and therefore the concentrations of A and B must decrease. And that's pretty much it for temperature and equilibrium. Hopefully this video is of some help.